Title's different.
Okay, we're going to get started. It's my great pleasure to introduce Mike Cushing from the University of Toledo. Mike got his undergraduate degree across the river at BU, and then he went to University of Hawaii for graduate school, which is where I knew him. And then he went on as a Spitzer Fellow to NASA Ames and the University of Arizona, and then had brief postdoc stints back at the University of Hawaii and at JPL. Is that right?
Yep.
And since then, he's been a professor at the University of Toledo. And Mike's an expert infrared spectroscopist who works on very low mass stars and brown dwarfs. And he's going to talk about his work with the WISE telescope, observing the coolest brown dwarfs, the Y dwarfs. Mike, take it away.
Thank you. Thank you for inviting me. I very much enjoyed my my day here talking to people. Obviously it's a vibrant community, and I really have enjoyed myself. So today I'm going to tell you about some of the work I've been doing looking for the absolute coldest brown dwarfs with the WISE satellite. These are the people that are involved with this work. The people in red are the sort of core members of the WISE brown dwarf science team. It was led by David Kirkpatrick for many years. I was a postdoc under him at JPL, but there's a lot of other names on here. The theorists that we work with, Mark Marley, Didier Simon, Carolyn Morley, they do a lot of our theory work. Adam Schneider is a postdoc who works with me, and much of the data that I will show you today he's been working on. We have a large HST program to follow up a lot of these objects. And I'll also be showing work from other people who are doing this. We're not the only ones, and so I put competitors in quotes because technically they are, but a lot of them I actually work with, so they're really colleagues as well. Trent Dupuy at the University of Austin, Kevin Luman at Penn State, Sandy Legg at Gemini, and David Pinfield and Jackie Faraday as well. So today, these are the three things I'd like to talk to you about. I'm going to do some brown dwarf basics and sort of motivate why it is that what I'm going to tell you today. I'm going to talk to you about WISE and the discovery and the early characterization of the Y dwarfs. We're still sort of in the very early phases of trying to understand these objects. And then I'll tell you something about some of the constraints we're putting on the low mass field mass function. All right, so the first part is sort of brown dwarf basics and motivation. The defining characteristic of a brown dwarf, of course, is that it does not fuse hydrogen in its cores. And so in no time in its life reaches an equilibrium configuration where the surface radiative losses are balanced by some energy being generated, right? It never reaches a main sequence. And so brown dwarfs simply cool as they age. So this is a figure from Adam Burrows' review article showing the theoretical evolution of various objects of various masses as a function of time. So we have effective temperature here, so hot, 4,000 degrees, the sun's up here somewhere, all the way down to 100, 200 degrees Kelvin, and time. So we have 1 million years, we have 1 billion years, and we have 10 billion years. Right? You start up here at 200 times the mass of Jupiter. Jupiter's like 1,000th the mass of the sun, so this is 0.2 solar masses. And then you work your way down, and what you see is that if you are a 0.2 solar mass star, you reach a main sequence. Your temperature and luminosity stabilizes, and you do this for like 20 Hubble times, right, before you run out of hydrogen. If you are something slightly lower mass, that still happens, and then eventually you reach a point here, which is about 80 times the mass of Jupiter, where you never reach that equilibrium configuration, and you simply cool off over time, and the temperatures just fall. And so we can sort of nicely divide this into stars up here and brown dwarfs down here. Some people like to make a distinction about planets happening at 13 Jupiter masses because deuterium is infused, and for proposal purposes, I use that as well, but for our purposes, they're just cold things, brown dwarfs. So you'll notice the sort of temperatures, right? We're talking at, maybe 1 billion years, we're talking thousands of degrees, 2,000 degrees down to, several hundred degrees. And so because of those low temperatures, brown dwarfs have very molecular rich atmospheres. So this is sort of a cartoon diagram showing you the log of the abundance relative to hydrogen up over here versus the atomic number, and various atoms that we talk about are sort of floating over here. And then in bubbles here, we have some of the things that can form from these atoms. And so, you know, carbon is in CO or methane, nitrogen is in ammonia or N2, oxygen, which I probably forgot to put on here, is in water primarily. And then you have refractory things like magnesium and silicon and aluminum, and they form these complex molecules. I mean, complex from our point of view. But they're actually dust, grains, Forsterite enstatite. So you get not only molecules, but you get solid things. And this chemistry actually evolves in time as either you move through the sequence of brown dwarfs, or you just take a brown dwarf and you let it cool off over time, right? So what this is the temperature pressure profiles for various objects of various masses. So we have the run of temperature and pressure within an atmosphere. So on the left axis here, we have the pressure in bars. So this is the upper atmosphere where it's low pressure. As you go into the atmosphere, you come down. And then we have temperature going from 100 degrees out to 10,000 degrees. And so as you go into an atmosphere, you go down and to the right. So here's the curve for the sun. Here it is for an M dwarf, an L dwarf, a T dwarf, a Y dwarf, and Jupiter. And I'll tell you what these letters mean in a second, but here's the temperatures that go with them, right? The dots here show you the photosphere, roughly speaking, where the light that you see emerges from. And so as you go to colder temperatures, you see they become higher pressure and lower temperatures, right? So molecules start to take over. There are two important chemical transitions that have to do with the carbon and nitrogen chemistry. So here's an equiabundance curve. So if you're on this dotted line and you're to the right, your carbon is primarily in CO. And if you're to the left of this diagram, your carbon is primarily in methane. And so right away, you can say, okay, well, L and M dwarfs probably have a lot of CO, and T dwarfs probably have a lot of methane. And I'll show you that in a second, and that's true. The same thing happens in nitrogen. You can go from being primarily diatomic over to ammonia as you go to the coolest temperatures. And so you have all of these molecules, and so they're going to dominate what the emergent spectrum of these objects look like. So here's a sequence of model spectra going from 3,500 Kelvin down to 400 Kelvin in black, and then the corresponding Planck function with the same effective temperature is shown in color, right? And so obviously as you go to colder temperatures, the Planck function shifts to longer wavelengths, but you can immediately see that these spectra are distinctly not Planckian, right? They look very much not like a Planck function. And so when you see things like this, people sort of sometimes have a hard time thinking about what does that really mean. Well, this is the sort of overall Planck function. And so you can see in the near-infrared, you're way super Planckian, whereas at other wavelengths, you're sub-Planckian, right? And so the spectrum is very different than a star. And you can see the chemistry changing. You've got water and CO in the hottest regions, the hottest objects, and then as you go to colder regions, the methane kicks in, and then as you go to even colder objects, the ammonia kicks in over here, and then we hope we see it down here someday. There's another level of complication, which is the dust. So in gray here are where the condensation curves for various species. So if you're to the right of the curve, you're in the gas phase. If you're to the left of the curve, you're in the solid phase. And so if you're colder than this line here, then you will form Al2O3, or iron, liquid iron, or potassium chloride clouds, or water clouds, or ammonia dust, right? You'll actually condense out of the gas and form this in the solid phase. And when that happens, these particles now feel a gravitational field. They will gravitationally sedimate out of the atmosphere, and they will form clouds at the intersection points of the photospheres. Intersection point of the temperature pressure profile and the condensation point. So these clouds form here. These kind of clouds form here, and then you've got water and ammonia clouds over here. And so immediately you can see, well, looks like L dwarf, the clouds seem to form right in the photosphere. So they're probably going to have an impact on what the spectrum looks like. These particular clouds intersect all the way down here in the T dwarfs, right? And the photosphere is kind of like up here. So those clouds probably don't matter, but those clouds probably do, right? So you have this evolving chemistry with more and more clouds forming. So here's sort of a cartoon of that, right? It's just sort of a summary. As you go from M to L to T down to, say, Jupiter, you pick up more and more and more and more clouds, okay? So you've got chemistry, you've got molecules, and you've got dust and condensates. The clouds have a really big impact on what the spectrum actually looks like. So here's a model of a brown dwarf at 1300 Kelvin. The black is the Planck function, and then the two models show a model where you are clear, you have no clouds, and then a model where you're cloudy, right? And they look completely different. I mean, yes, the overall shape is sort of right, but the blue clear one has much more jagged molecular bands. The molecular bands are much deeper, Whereas when you have a lot of dust in the atmosphere, it sort of tries to push it more towards a Planck function, right? And so, this is something we have to contend with if we want to infer the physical properties of these objects, right? You can't just go on, oh, there's a really deep molecular band here, so it's got to be cold. Well, maybe not, right? It can be just as cold, but if you've got a lot of dust, that band is going to be much weaker. So sort of the summary of this part is, brown dwarfs have cool, molecular-rich atmospheres, and they evolve as they cool off. So the first brown dwarf that was discovered, and I'll say first in quotes, was Gliese 229b. And actually, I think the anniversary of the actual first day that Ben Oppenheimer viewed it at Palomar, actually at the telescope, was like 2 weeks ago or something. So it was like 20 years ago. So this was the first one that the astronomy community said, yes, you finally got one. The brown dwarf community will fight over what the real one is. But this was the one where everyone said, yes, yes, you have one. And the reason why is because its spectrum was so distinct, right? So here's its spectrum compared to other things that we knew. So this is in the near-infrared, 1 to 2.5 microns. Here's what our sun looks like, or a star like our sun. It's basically a Planck function with some weak atomic lines. One of the coldest stars known at the time was VB10. It's got some water and some CO over here. And here's 229b, right? Completely different. It has these deep methane absorption bands. And in order to be cold enough to have methane, you have to be substellar, right? And that was the linchpin of this argument, and that's what really made this one stick. And you might also, although it's fortuitous, it kind of looks like the spectrum of Jupiter, right? The reason why they look like that is not the same physics, but it looks similar, which was another thing that helped sort of push the point. So after the discovery, 2-mass Sloan kicked in, and literally hundreds of these things were found. And with spectra that look so different than anything else, we had to add 2 new spectral types to the spectral sequence, the L and the T dwarfs. So the Ls are typically classified in the red optical from 6,000 to 1,000. Here's an M dwarf. You see lots of titanium and vanadium oxide. That's the hallmark feature of an M dwarf. As you go to the later types, those go away. Titanium, vanadium are refractory. They turn into dust. They turn into clouds. You lose them from the gas phase. You lose the opacity. You lose the band heads. Right? You start to pick up hydrids and weird things like rubidium and cesium. Right? Whoever thought you'd see rubidium and cesium in a star. Also, the potassium doublet here becomes absurdly pressure broadened. Right? This is due to the fact that you're looking so deep into the atmosphere that the pressure broadening is literally hundreds of angstroms wide. And so the potassium line actually controls a lot of what's going on this red wing. And then, of course, in the near-infrared, you pick up the methane, which is the T dwarf. So 229b was the sort of archetype of the T dwarfs. So this is where these things land on this sort of temperature diagram. So the L dwarfs sort of go from 2300 to 1400 Kelvin, and the T dwarfs go from like 1400 to maybe 500 Kelvin or so. And so, the question for a long time was, is there anything colder than that out there, right? And so, it's sort of, is it T dwarfs all the way down, or is there something else beyond that we can talk about? And this isn't just stamp collecting, right? It's not just a question of who gets to add a letter on to the Morgan-Keenan scheme. There's physics here as to why we want to study these things. The first is that these atmospheres can tell us a lot about ultra-cool atmospheric physics, right? And so I've already shown that it's a very complex environment where you have molecular formation, you have condensate formation, you have to worry about how those condensates fall out of the atmosphere, how the clouds, how the mass is distributed in the cloud, what the particle size distribution is. There's a lot of physics that goes on here. And these atmospheres are nearly identical to gas giant exoplanet atmospheres. And so it is infinitely easier to study an isolated brown dwarf sitting in the field than it is to go and look at a Jupiter sitting next to some bright wonking G star, right? We want to do it for other reasons, but just to study atmospheres, it's just easier to do it here. And to motivate the cold ones, this is a simulation that was done a couple years ago for GPI, which is the Gemini Planet Imager, which is actually on its first commissioning run, which is wonderful. This is an instrument that was built by Bruce McIntosh. It's on Gemini looking for planets. So the rows here are just various selection criteria of the planets they would expect to find given their underlying assumptions. So don't worry about the rows. The point here is to look over here at the effective temperature distribution. And you can see here that in the black curve, they're all peaking around 400 Kelvin, right? So if we want to actually understand what it is that they're finding when they go out and they find some object sitting around some star, they're going to go and use models and say, oh, it's this mass, it's this, it has this radius. You'd like to think that those models have been, tested a little bit. And brown dwarfs, and particularly these cold brown dwarfs, are the right way to do this before that happens. The other thing is the space density, or what we call a mass function of cold brown dwarfs. It can constrain brown dwarf theories, at least in principle. So the problem with forming a brown dwarf from our sort of standard genes collapse is that you have to have extremely high densities, right, for the cloud to collapse and form a brown dwarf, and that's a difficult thing to do. And so there are various ways you get around that. You may talk about turbulent flows collapsing, or maybe you let stars form like normal and then they get ripped away from their gas clouds. They get cut off from their accretion, and that makes it a brown dwarf. Or maybe you just have a direct collapse of a disk and then it gets tossed out, right? So there's all these other ideas about how you would form a brown dwarf, and these have to predict how many you would make, right? And so if we can go out and observe how many there are out there, we can then, in principle, choose between these various models. I sort of all said all that, so I guess I'll keep going. So let's talk about why. So we've talked about, you know, what brown dwarfs are, why we would want to go find these cold things, and so let's go find them. So the way we're doing this is with the Wide Field Infrared Survey Explorer. This was a NASA mission that was launched in 2009, late 2009. The PI is Ned Wright at UCLA. Normally, I would assume most of you probably heard about WISE. For years, I was sort of giving like an intro to WISE, but I figured it's been around enough that I won't go into too much detail. Basically, it's an all-sky survey at 3.6 and 4.5, 12, and 22 microns, and we call these W1, W2, W3, and W4. This is sort of like Spitzer 1 and 2, and like IRAS 1 and 2, for the people who know what IRAS is. The latest data release is called All WISE. And it consists of about 18,000 2-degree by 2-degree atlas tiles that have co-added all of the data together that were taken, and a source catalog of about 750 million sources. The beauty of AllWise is that it also includes apparent motion measurements. It turns out that WISE was actually able to scan the sky twice in its mission at the two shortest wavelengths, W1 and W2, because it can operate, those channels can operate at ambient temperature in space. You don't need to be cooled by the cryogen. And so we have a 6-month baseline, and so we can actually measure the proper motion, the apparent motion. And of course, apparent motion is proper motion and parallax, and if you're nearby, you can't distinguish those two with 2 points, so we call it apparent motion. So this is wonderful. You can go in and look for things that are moving on the sky. Here's a nice all-sky image from WISE, right? One of these beautiful 3-color images, 3.4, 12, and 22. So you see all the starlight and all the dust here. So the reason why WISE is so good at finding these, it's not just a function of the fact that it's looking at mid-infrared wavelengths, which is where the Planck function peaks of these things. It's that it was tuned specifically to find cold brown dwarfs. And so if you look where the bands are in WISE, you can see that W1 is set about here, and W2 is set about here. So in the coldest brown dwarfs, say down here at maybe 1,000 or even 400 Kelvin, right? There's very little flux coming out here. This is due to a big methane band, a fundamental methane band. And then right here, there's an opacity hole. There are no molecules that absorb at those wavelengths, and so you have all this light trying to get out in the infrared with nothing to get in the way, and so it all pours out at 5 microns. And so by looking at W1 minus W2, a color or flux ratio at these wavelengths, you can look for things that are very, very red, right? As opposed to stars, which look more like this, which are very, very blue, right? And so that's what this sort of shows here. This is a sequence going from M down to Y, if you will, the cold things. So they look very blue here because you're just basically doing a Rayleigh-Jeans tail. And then as you move through the L's and into the T's, they start to look green, right? Because we've color-coded blue, green, red. This is a sort of slightly more quantitative way of looking at it, W1 minus W2 versus W2 minus W3. So it's 3.5, 4.5, 4.5, 12. This is where all things that I don't care about live, like stars and galaxies and interesting things over here. And this is where at the time, T-dwarfs, because we didn't have Y-dwarfs when they made this figure, we thought would live. So sort of 2 and greater, right? And this is exactly where we're finding these things. So the predictions were not too far off. So the one that really got our attention was this object here, WISE 1828, 2650. I think you can see it, right? It sort of sits right in the middle there. It's this nice little green thing here. It has a W1 minus W2 of greater than 4. Because of that methane band at 3 microns, we don't get a lot of light out there, and it's not like this is a massive telescope where we're integrating for hours. So you get a lot of upper limits in that channel. So it's at least 4, but probably more than that. It's J minus H is 0.7, which is actually very red for a cold object, and I'll show you that in a second. And it's J of 23.5. So this is faint, right? This is not, you're not doing this from your backyard, and you're not even doing this from IRTF, right, in Hawaii. It's so faint that we need HST to get a spectrum of it. And so here is its HST spectrum. we published an initial one in 2001. This was, it was actually contaminated because of WFC3 is a slitless spectrograph. And so if you don't get the roll angle just perfectly, some annoying star off the field or just on the edge of the field will put its spectrum on your spectrum, right? And if you're a galaxy person, who cares? Throw that galaxy out and you have 20 other redshifts. If you're a star person, you want that one object, right? And that's the problem. So we had to go back and get a better spectrum, and this is it, and we're working on this now. And so it's shown here in black, and then on top of it in red is shown the spectrum of a T9. So this is one of the latest T-dwarfs known at the time, right? It's a really famous object. And you can see that they don't look the same, right? 1828 is not a T-dwarf. And specifically, this pattern of sort of Y down, J up, and H down is consistent through the whole T-dwarfs, right? And that is just not the case here. The peaks are roughly the same height and units of, that should say F lambda there. And so based on that, remember we had this contaminated spectrum, so it was hard to fit a model on that. But we knew that even with the contaminated spectrum, those peaks were roughly the same. And the fact that its color is insanely red, this J minus W2 is like 9, we put a limit of like 300 Kelvin on this object, right, which is the temperature of the air in this room. So we were very excited, and we had a Y dwarf, right, because it did not look like a T dwarf. It was a different object than a T dwarf. So Y, you might wonder, would we use the word Y? This is Y. That's a lot of Y's. Sorry, I didn't plan that actually. This is a table from David Kirkpatrick's 1999 paper when he defined the L sequence, and it has to be the only table in science where the first column is the letters, but there it is. He went through each of the letters and said, can we use it for a new spectral class, right? And for A stars, obviously, for A you can't because we have A stars, right? And O stars you can't because we have O stars. And what he showed was that he thinks that there were 4 letters that we can actually use. We can use H, L, T, and Y. And I don't remember what the rationale for L was. I think initially Eduardo Martin suggested it for lithium because we could see lithium in these objects. And then I think it just stuck. And then the next one we figured, well, it's got to be colder, so we'll do T. And so the next one is Y, and that's YY, right? So it's not any interesting thing. And yes, it's hard when you try to say a white dwarf or a Y dwarf, and we know that, but our community has been saying Y dwarfs for 10 years now, so it was going to be a really hard thing to try to change that. Currently, we know of about 23 Y dwarfs, 20 of which are spectroscopically confirmed. And I'm sort of being a little bit sly on that because you can't know it's a Y dwarf until you see its spectrum. But there are other reasons why we think these are. So here's the 21 of them that we have, discovered primarily by our group, but by other groups as well. And then we have 2 over here that have to be Y dwarfs. They're cold enough, they're faint enough that they have to be Y dwarfs. But they're just too faint to get a spectrum of. We can't even do it with HST unless you want to give us like 100 orbits for one object, which I'd love to do, but I don't think I'm going to get that through the TAC. The first one is WD0806. It was discovered by Kevin Luhman. It's a companion to a white dwarf star. It's a J of like 25, right? 1828 was 23.5, and it was like 15 orbits to get that spectrum, right? So do the math. And its effective temperature is like 300 Kelvin, 250 Kelvin. The other one that is really quite exciting is WISE 0855. This one was just recently discovered by Kevin. It's the 4th closest star system to the sun, so it's at like 2 parsecs. We still don't have a limit. We still don't have a detection at J. It's 24-ish. Someone claims a detection. And we think it's like a 250 Kelvin brown dwarf. So these clearly have to be Y dwarfs. So we're sort of at 23 is sort of the number. So you compare that to the thousands of L and T dwarfs we have, right? We're nowhere near having the statistics we have as we do for L and T dwarfs. Here's the sort of Y dwarf sequence as we have it right now. It's rather short. This is work that my postdoc has been doing. So these are all HST spectra. And so you have the sort of the T8, T9, and then we go Y0, Y1, and then we have this 1828 here, which we're saying is sort of greater than or equal to Y2. So it could be Y3, it could be Y4 until we get more objects to fill the sequence in. We just don't know. It's the width of the, so the difference here is the J-band narrows. So this is the J-band right here. And if you look, this goes down, down, and keeps getting narrower. And I didn't plot it, but if I were to put them on top of each other, normalize to J. Yes? Yes. This one's a problem child. We'll get to this problem child in a bit. Yes, absolutely, I agree. So the other thing is that the Y, J, and H peaks seem to move towards unity. So here it's that sort of Y, J, H, and as you go down, they get closer and closer together. And then the peak of the Y band, which is this thing here, seems to shift towards the blue until we get this sort of very square-looking shape, and I'll talk more about that in a little bit. The colors seem to transition at the TY boundary. So this is a Y minus J, so 1 versus 1.2 microns versus spectral type. And you can see that, the T's are sort of just hanging out at 1.2, and then all of a sudden things change rather dramatically right at this point. And the same thing happens here in J minus H. They sort of get bluer, and then they plateau, and you might argue there's a turnaround, although I wouldn't necessarily say that. There's a lot of scatter in this data, and the errors are quite large, but at the very least, it plateaus, right? This drop is clearly stopping here at this boundary. And the reason why we think that's happening is the formation of these clouds, the Na2S and the potassium chloride clouds. When you take away potassium, right, from the gas phase, you lose the opacity from potassium. And that doublet down at 7,700 angstroms or so goes away, and now you can see deeper into the atmosphere, more light comes out, so the color turns, right, and becomes more blue instead of being very steeply red. And then the reason why the near-infrared is doing this is because the increased opacity from the cloud. So it's not, the clouds not only muck with the chemistry, and so that's what's going on here, but they also add their own opacity, right? These particles absorb, they scatter, and they change what's happening in the spectrum, right? And so that's what's causing this flattening here. Y dwarfs are cool. They're less than 500 Kelvin. I won't show you the fits to the model atmosphere fits. They're not pretty, and I'll show you that in a minute. There's one that's really not pretty, and I'll get into a little bit more detail about that. But the consensus using various models and various techniques is that these things are very cold, and so this is sort of our take on this. Here's the T dwarfs, and then as you move down to colder temperatures, they get colder. And if you want to know why this is happening, I can explain that later. But sort of look from T6 down, they just sort of collapse down here. And like I said, this is people come to this conclusion using photometry, using other techniques, and other spectroscopy. Y dwarfs are very faint. I've already sort of mentioned how faint they were from an apparent magnitude and absolute magnitude. They're very faint, especially in the near-infrared. So this is work by Trent Dupuy and Adam Krauss. They went out and got Spitzer imaging to do parallaxes of these objects. And they have their absolute magnitude versus spectral type plots of Y, J, H, K, 3.6, and 4.5. And you can see that these things are very, very faint, 22 for an absolute magnitude, right? You might notice there's 1828. Right? So this sort of happens here, and then why, wait a minute, why is that up here, right? Yet again, another sign of a problem with this object. And you might even argue that over in the H-band, right? If this is dropping down, why is this one so high? Same thing here. So it looks like this object is a little bit overluminous. Y dwarfs also have very, very red near to mid-infrared colors. So this is the J minus W2. So this is 1.2 microns versus 5 microns, so a big lever arm. Right? And what you see is, as you move through the M's and the L's, things happen, chemistry, clouds. And then as you move into the T's, it just goes extremely, extremely red, right? And we're up to sort of like 10, 11, 12 for some of these cold objects. In particular, I want to focus on these last two guys. And I put the break here because of the spectral type problem that we're having. And these guys don't even have spectra, so we can't really type them. So be careful about inferring too much about this trend. They could be over here or over here. But I want to focus on these guys because these are the ones that are sort of the outliers, right? They're above sort of 10. And as I mentioned, these are sort of the three ones that we think are lower than that 300 Kelvin, right? Or at least there's some indications of it. In particular, that this one everyone agrees is, this one everyone agrees who is, not everyone agrees with this one. And so, they're faint, they have very, very red colors. And I'll just point out what I pointed out a second ago, which is that Y1828 appears overluminous, right? In all of these features. In all of these figures. So what are the possible ways around this overluminous problem? One possibility is that it's just hotter, right? So Dupuy and Krauss would argue that actually no, it's just hot. It's like 600 Kelvin. It's not 300 Kelvin, it's 600 Kelvin. And how did they do this? Well, they went out and they built a spectral energy distribution. They know its distance. They can get a bolometric luminosity, sort of, if they use atmospheric models to fill in 50% of the flux. But that's what we're working with in our field. So they have a bolometric luminosity. Using Stefan Boltzmann, if you knew the radius, you could get the effective temperature, right? So the problem is, what is the radius? The beauty of brown dwarfs is that due to their equation of state, due to the competing effects of sort of Coulomb forces and electron degeneracy, the mass-radius relation is basically flat across the entire brown dwarf regime for oldish brown dwarfs. And so we can just say that the radii is Jupiter, because Jupiter's sort of at the tail end of this. And even if you account for some slop in that, you still get a very hot temperature of like 600 Kelvin. So maybe this is just a hot one, right? Maybe it's a T-dwarf, but something is really weird going on in the near-infrared, possibly. Sandy Leggett has suggested that it could be a binary. You know, the first thing you think of when you see something overluminous in a sequence is, well, we'll just make it a binary, right? But in some of the sequences that we see, it's not 3/4 of a magnitude, it's like 2 magnitudes, right? Which is, you know, that's a lot more than just a binary. So that one is still out there, but we don't know. And then the third thing is maybe some new physics. And I don't mean new as in, you know, we're discovering new physics. We're just applying, you know, we're just not using all of physics to understand these things. And so maybe it is that this thing is just an oddball, and we find more of them, we'll see a sequence, and our preconceived notions of what it should be will change, and it will just fit the sequence very nicely. This happened in the L and the T dwarfs, actually. We would have thought they would have evolved a certain way in color magnitude space, and they didn't. And we had to say, well, our models don't work for that, and that's what it is, right? And so maybe that's what's going on here. So we don't know. But we have the data, and so let's see what the models do with this object. So here is all the data we have for this object. So here's WISE 1828. There's your spectrum, and then we have 2 Spitzer points here. So this is 3.6 and 4.5 microns, right? So that's our spectral energy distribution for this source. Not so impressive. So what we want to do is compare atmospheric models to these data and see how well they fit. And so what we did is we've been using the Morley et al. Models. These are the latest generation from the Marley group. They have a range of temperatures and gravities. We assume solar metallicity. They have various clouds. They have various ways of dealing with the clouds. Don't worry about that. And then this will sort of come back in a second. We assume equilibrium chemistry, and I'll explain why that's important in a second. In order to compare models, which are one-dimensional model atmospheres, right? So the emergent flux at the surface of a star, you have to multiply by the radius divided by the distance squared to compare directly to observations at Earth. So we have this sort of scale factor here. And the way I've been doing this is sort of a Bayesian way, where you start out with a likelihood function, which is the probability of your data given, say, the atmospheric parameters and the radius and the distance and your uncertainties. You have some priors on that knowledge of what you think those would be. So maybe, for example, the radius is like Jupiter, roughly speaking, with an error bar. You know the distance to within, you know, a parsec. You push that through Bayes' theorem, and out pops what you really want, which is the probability of your model given the data that you've observed, right? So we fit this in a couple of ways, trying to figure out what's going on with this source. So let's imagine, instead of having a prior on R and D, let's just say we don't know R and D. It's just a scale factor. It's just some unknown scale factor, right? So if I fit for that scale factor in this process, this is what I get. I get an effective temperature of 275 Kelvin. That's cold. The data, the model's sort of kind of okay, right? I mean, it has bumps where it should, but it's not the best fit. It misses very badly over here in the methane. It's very hard to have a lot of flux coming out at this wavelength when you're this cold, because all that methane is sitting there. And this is a real sticking point, which I don't understand. And then this is not so bad. The issue that you might see, one big issue, is this wonking thing over here, right? That's ammonia in the models, right? And for a long time, we had been hoping to see ammonia in these data, and we still have yet to see it. There is a little feature that sits in our data that we thought could be ammonia, but it turns out it's not at the right wavelength, and we've scratched our heads hoping that we made a mistake and it would shift over and line up and we could announce we have ammonia at the near infrared, but we just can't get there. So we don't see ammonia. And the reason why these models have so much ammonia is because they're assuming equilibrium chemistry. It turns out that there's mixing in the atmospheres of brown dwarfs, right? Clouds require 3 dimensions to form, and so you can actually take, say, for example, diatomic nitrogen-rich gas in the deep interior of the atmosphere, mix it up into the upper atmosphere where it wants to turn into ammonia in equilibrium, right? But if you mix it faster than you can convert it into ammonia, you'll end up with an overabundance of ammonia, an overabundance of diatomic nitrogen and an underabundance of ammonia, right? And so you turn mixing on and the ammonia bands get weaker. And so we think that if we do that, that has not been included in these models yet, that this will go away and it will fit better. The other issue is that the ammonia really impacts what's going on the left and the right side of the J band here and the H band. And so maybe the fits will get better here as well. And so I'm pushing Carolyn pretty hard to try to get this incorporated into her models, although it's probably not going to happen. So the summary, the problem is, okay, so maybe it's not such a bad fit. Maybe the near infrared is the non-equilibrium chemistry, and maybe the 3.6 is just a bad data point. So here's the sort of summary of it. That scale factor gives you a value of 0.3 R Jupiter over parsecs, and we know the distance, So that means it has to have a radius of about 3.3 Jupiters, 3.3 Jupiter radii. That's too big, right? I told you that the mass radius relation is sort of flat. That's just unphysical at this point, right? So we might have had a good fit, but it's unphysical, so that's not so useful. And even if, and it's not even a good fit because chi-squared is like 10,000 and I have like 200 degrees of freedom, right? So I don't even know, I mean, I know what that p-value is, right? It's epsilon, and epsilon is really close to 0. So now let's imagine I fit with R and D. So now I put a prior of Jupiter radius plus or minus like a little bit, and then I know the distance to it, and I fit that, and this is what I get, right? So I get the same sort of mess going on down here. It's 300 Kelvin, similar surface gravity. Same problems over here, but now I get nowhere near these Spitzer channels, right? And this underlies this problem with this object, right? When we first had this object, we had no distance information to it, right? All we had was the color, the shape of the spectrum, and then this big whopping color. And so that's why we came up with 300, because we were looking sort of at this information, right? Trent Dupuy, who came up with the hotter temperature, is primarily worried about this because he's doing luminosities, right? And this is where all the energy is coming out. So he's getting a hotter temperature based on that point. And this is the problem. We cannot simultaneously fit these two things. And so, you know, my delusional thoughts at night are well, maybe there's some dust cloud around it, right? Have to be a really big dust cloud to be emitting, but, you know, maybe there's some Planck function doing this that's messing this up. Or I don't know what, right? I mean, maybe there's other physics that are going on in here that we don't understand yet. But if we do this, so let's even assume this is a good fit, which it, of course, is not. Out of this probability distribution, you get the wrong distance, right? So you give it a prior, which has, you know, 11 plus or minus 2 parsecs, but, you know, it gets out to 6 parsecs, and that's where the probability distribution peaks. So that's not right. It's too far, it's too close, right? So we get the wrong distance. So even if you buy that crappy fit, you don't get the right distance, and we know that, so that's wrong. Another possibility that I tried was to do Sandy Leggett's binary star. I used the radii from Didier Simon's evolutionary models. It's not quite a good comparison because those models are not self-consistent with the atmospheric models, but it's what we got. So if I did that, I just built a bunch of binaries with the model atmospheres and tried to fit it. I could do it. I would show you it. It looks just as bad as the other ones. 250 and 300. But again, we get an unphysical distance and also an unphysical gravity. So a log G of 5, you can't even evolve a brown dwarf there. You can't be 250 Kelvin and a log G of 5. You can make a model atmosphere there, right? Because the gravity just sets the pressure, right? So I can do that radiative transfer, but I can't start a brown dwarf off and let it evolve to that temperature and gravity. So now I'm not only getting the wrong distance, but the wrong gravity, right? So binary, at least with these models and this method, doesn't seem to work. So is there a way out of this? And a paper just came out on AstroPH that I'm really praying is the way out of this, which is this recent paper by Sandy Leggett. She's been getting a lot of infrared photometry from Gemini on NIRI. So here is a absolute W2 versus J minus W2 diagram, right? So this is that one where that object is really red, and then here's 0855, and there's 0806. So these are these 3 red ones. And for a long time, we sort of had these objects here, not, well, I should say, and then we had this one. And this is why we say it's overluminous, right? Because if you assume that this is some continuum, that's way overluminous. But her new photometry is saying, well, maybe this is just a plateau here, right? Maybe there's something going on here, right, where the clouds are not behaving like the models suggest, right? There's nothing that says that the clouds have to behave like Carolyn's models. They don't behave that way at the L to T transition. In fact, we still don't understand how a brown dwarf goes from the Ls to the T dwarfs. We think it has something to do with the clouds either having holes poked in them or they're just disappearing by some unknown physical mechanism, but just a regular set of clouds will not reproduce that transition. So maybe that's what's happening here. Maybe this is really what's happening in the universe, and we just need to fix our models. Maybe there's another thing going on, and that's what I'm hopeful for, because we'll learn something, right? Just like we learned something at the L to T transition. So this object has been annoying, but hopefully it's pointing the way to something new about the clouds happening down at these very, very cold temperatures. All right, so the last piece of the talk I want to talk about is the constraints on the mass function. So as I didn't show you earlier, but I will show you now, the mass function, of course, summarizes how molecular clouds turn their gas into stars, right? And so if you want to understand the process of star formation, you have to be able to at least reproduce that, right? Because that's the sort of basic thing. Here's what we know about the mass function in a very, very schematic way. So it's, so this goes from 0.001, so this is like Jupiter down here, up to 10 solar masses. And then just think of this as log of the number of objects, roughly speaking. If you parameterize this curve as power laws, so dn dm is m to the alpha, you see here we have this sort of constant slope. This is known as the salpeter slope. There seems to be this break around roughly a solar mass that sort of turns over. And the question becomes, what happens down here? There's a lot of work in star formation regions that suggests it turns over, and it most certainly does. But we'd like to do it in the field as well, right? It'd be nice to make sure that everything is consistent, that we've dotted our I's and crossed our T's. And so, what is the slope down here? And can we figure out what the minimum mass of star formation is, assuming that brown dwarfs form by fragmentation of molecular clouds, which might not be the case. So in order to do this, we need to go out and collect a volume-limited sample of these things. So this was in David Kirkpatrick's 2012 paper. So here's the 8-parsec sample of objects. M dwarfs, wow, there's a lot of them out there, right? And then there's not a lot of brown dwarfs. And so you may have seen, maybe 10 years ago, this figure that Robert Hurt made with the scale, right? The scales of justice with like the solar neighborhood stars on one hand and the brown dwarfs on the other hand. And they sort of had equal masses. And that's just not, that figure's not right anymore, right? We know now that there aren't that many brown dwarfs out there. So we sort of have this volume-limited sample. We've pushed it to a little bit longer, but this was just to show you how few brown dwarfs there are compared to stars. The ratio is like 6 to 1-ish. And this is, of course, incomplete because we're still looking for them. We're still trying to measure distances to them. We haven't gotten parallaxes for all these things. It's a very hard thing to do. And the issue further, besides not having a volume-limited sample for all of these things yet, is how do you measure the mass of a brown dwarf, right? It's not like you've got some planet that you can watch going around these things to get the mass. Typically for stars, you can go out and observe a luminosity and convert it to a mass with a mass-luminosity relation, right? And the reason why that works is because you have a main sequence, right? And so here's the same sort of figure, but now it's bolometric luminosity. So here's a 0.2 solar mass star. So if I went out and measured it and it had a luminosity of that, I could say it's a 0.2 solar mass star. Well, with a brown dwarf, I measure a luminosity of, say, 10 to the minus 5. Well, it could be a 1 Jupiter mass object at 1 million years, or it could be a 60 Jupiter mass object at 10 billion years, right? They don't come with age dates. And it's hard enough to age dating stars, right? We have zero ability to do that with, well, not zero, epsilon ability to do that with brown dwarfs. So how do we get around that? We forward model a population of brown dwarfs, and then we compare it to what we see. So you start out with an assumed mass function, so some power law. We assume some formation history, say uniform over the age of the Milky Way. It turns out it's relatively insensitive to whether it's uniform or stochastic or some other exponential decay. We then simulate, by drawing randomly from these things, a population of brown dwarfs with a certain mass and age, right? We take those values and we say, okay, we have evolutionary models. Let's assume we know something about how these things change in bulk. We can then get a simulated population of effective temperature and gravity, right? And then we ask, is that what we see, right? And if it's what we see, then we have some confidence that all of this is right. This is what it looks like when you run one of these simulations, right? So here we are, effective temperature, so 2500 Kelvin down to 432, 100 Kelvin, 200 Kelvin roughly. And now I've got it in sort of slightly weird units, but number per 100 Kelvin within 10 parsecs, right? So, not a lot actually here. And what you see is that the mass function, if you assume that the mass function over the entire mass range of brown dwarfs is just a power law, a single power law, the various power laws diverge the most at the lowest temperatures, right? So it's most easy to pick out between alpha minus 1 of 0 and 1 out here than it is down here, right? You don't want to do it down here because they all overlap, whereas you have a shot of doing it over here, right? And this was to show that in principle, if we had enough objects, you might be able to start picking off the minimum mass, but we're nowhere near that. In fact, we're nowhere near really getting the shape of the mass function right. So here's what we have so far. So this is sort of zoomed in on that upper right-hand corner. The colors are the same, so alpha is +1, 0, and -1. And here's where the WISE data is pointing to things right now. So this is sort of roughly complete. This is probably incomplete at this point because we know it's incomplete because we're still looking for parallaxes for these things. And so it looks like to us that, yeah, we could probably rule this out. We're not going to have this many brown dwarfs, but a simple power law doesn't seem to really fit the data. Even if you leave this here and then just jack this up in some uniform way, it doesn't really fit any of these models very well. And so it's very possible that, you know, we have to have a more complex model for how brown dwarfs form. And in fact, other people would argue that it isn't fragmentation of molecular clouds. Because it's off by, you know, whatever. This one's at 2, 3, 4, and this is, you know, starting at upwards of 10. And then this is upper limit, so this one's going to go up, and this one's going to go up, and the shape is wrong, right? So alpha equals 0, sort of flat, and then turns over. They will in... Yes, that's right. They will go up because, well, I can't guarantee because I don't have parallaxes, but photometrically, we have objects that we think are within a volume that this will impact. And so it's just a question of actually getting the parallaxes to put them at the distance we think they're at. We can do this photometrically, and we can put more of them in there, but we don't want to do that because binarity, other issues, we don't, you know, we want to get the parallax. So we know this is going to go up. It's not that we've run out of things to find. We have a huge parallax program, and I'll talk about that in just a second, to find these things. So it will change. Yes, I agree. That's why I think a single power law is not the right answer. It's also very coarse, right? I mean, and this is a hard game, right? This forward modeling assumes a lot of things. These evolutionary models are mostly right, but not perfectly right. This is a hard thing to do, right? So I mean, you know, it's sort of gross, huge statements that we're making. We're not going to have this many brown dwarfs, right? We're just, you know, you're not going to get up here from these guys. We're pretty secure in that. Am I going to tell you what the actual slope of the mass function is from this data? Probably not.
But when you did the modeling,
Yes.
the black curve.
Yes. No, the black curve is data.
Oh, that's the data.
Yeah.
Okay, that's the data.
That's the data. And then the models are the curves. They had the same colors as this. So all I did was zoom in over here.
Right, but you have the thing that you pointed out just a little bit earlier, that for a given temperature,
Yes.
you can have many different ages giving you.
That's right.
You know, different masses.
That's right.
The same thing. So
That's right.
How does the model then go and make the prediction? Does it assume a certain age range?
No. So remember, we're plotting. This isn't a mass function. We're plotting a temperature distribution. So over here, you could have an old object and a young object.
Right, but I thought you were putting a mass function. I thought the alphas were the mass function.
The alpha is how you start it, right? You generate masses and ages. You generate a table of masses and ages. Then you use those in evolutionary models to convert from mass and age to temperature and gravity.
Right, but you must have to then assume some kind of age spread among them.
Yeah, we assume a uniform age, right? And it's relatively insensitive to whether we do it exponential decay or stochastic star formation events. Yeah, so it's a temperature distribution because we can't measure the mass, right? It's the only way around it at this point. So we still have things to do on this, mostly getting parallaxes to really fill this in, and then we can really start talking about this. And Pavel Krupa just came and gave a talk to us, and he has some very interesting ideas about brown dwarfs are actually a separate mass function, and we're just seeing them sort of overlapped, right? Which is a whole new thing that I'm going to have to go think about. So this is in no way an answered problem. So just looking to the future, obviously, for example, we want to measure the parallaxes to these things to start filling out this volume-limited sample so that we can understand these objects. Also, we can start filling in those absolute magnitude color diagrams to see really is there that flattening. This morning at the lunch talk, I talked a little bit about weather of these objects. These things have clouds. They're patchy. You spin it up, and in integrated light, you're going to see variability, right? And by looking for variability, you can then, in principle, infer things about what's going on the surface of these objects. And so I have a large Spitzer program doing that. And then the thing we're kind of excited about now is the fact that WISE has been turned back on. The asteroid folks at NASA are worried about us getting hit, and WISE is a very good asteroid finder. And so the planetary division of NASA funded turning WISE back on for another 3 years, which is great. The problem for us is that we are looking for very faint things, and we like co-added images. But asteroid people don't care about co-added images because they want to see things move, and so there's no money to do the co-adding. And so all WISE is sort of was the end. It was the 6-month baseline. Now we have like a 5-year baseline. So in principle, we could find things that are moving much, much slower, which would be fabulous. But we don't have the infrastructure. We've tried. I shouldn't say we. The WISE people have tried multiple times to find funding for that, and every time the panel comes back and says, wonderful science, no money, sorry. It turns out David Hogg and his collaborators actually wrote some code to co-add WISE images, and you can take it and co-add all the data and make Atlas images just like all WISE. And so we're going to be starting to do that. We're going to co-add all the 4th-year data for this thing, and then blink images to look for things that are moving. And the hope is, just like Kevin Luhman found that very, very nearby object by its proper motion, that we will find new missing members of the solar neighborhood by their proper motion. So that's what we'll be doing for the next couple of years. Okay, thank you.
Questions? All right, John.
So you were talking about maybe adding in fixate to get better matches to the Spectra. You said you're pushing Carolyn Morley to do it, but then you suddenly got very pessimistic that she'd be able to do it. She seems to be has the most sophisticated models and the most complete knowledge of what should be going on in there. So why the sudden pessimism on that?
It's because the issue with that group's models is that in order to do it self-consistently, you have to take into account the chemistry as you generate the temperature pressure profile of the atmosphere, because it can change what's happening in the atmosphere if the opacities are changing. All of the non-equilibrium chemistry work that has been done by that group previously, it's a post-processing. So they generate temperature pressure profiles in equilibrium, and then when they run the radiative transfer to generate the spectrum, they tweak the chemistry. And they've convinced themselves that it doesn't impact the emergent spectrum dramatically. And so it's okay. But at these cold temperatures, it matters. And it is not a simple thing to get that into the code. And it's the way they do their radiative transfer. They use K coefficients, which means you have to generate these things from their literally tens of billions of molecular lines. And you have to do this at all temperatures. It's a lot of work. And the motivation is not there yet to do that. And she doesn't want to spend her time doing that when she could be doing other cool things. Even though I think it's important, we all think it's important, but she has a career to run, and so she wants to do something else, so she can do something else. So I don't know, honestly, when that will ever get done. It kind of worries me, because the Marley group is a very prolific group in this community. They have, I would argue, some of the best models out there, and so this is, unfortunately, a hole in their product. But they are severely manpower limited, and they need to find someone who's going to do this, and they just don't have that yet. So that's why I got pessimistic.
Yeah.
Two general questions. The first one is, can the presence of an unseen brown dwarf mimic the effect of I don't know, debris disk or dust around the star? And the other question is the effect of rotation, because these guys should have a few hours rotation rate on the spectrum.
Yes. Okay, so the first question, no. In order for it to be cold enough to be hidden, so that we don't see it, obviously, the shape of the spectrum is just too insane to do that. And I should note that Sandy, I believe, when she built her binary, she did it with data, right? So she was trying to find binary, individual objects that she thinks are individual and merging them to make this object. I was doing it by the models, and the models just can't get there. So no, is the short version. They're just not Planck enough to do it. And just adding a 250 Kelvin thing down there, because it has a lot of 4.5 micron flux, that's true, but in a relative sense, it's all way down from, say, a 300 Kelvin object, right? Because we're still talking about, it's just energy conservation. So no, on that front. The rotation, that's a great question, and I have no idea what that would do to the spectrum. We do see evidence for variability at the mid-infrared. We see it in photometric bands in Spitzer. So that's one of the things that we're working on now. It's at levels of a few percent. So we do see variability there. What it would look like in the near infrared, I really couldn't tell you. Mostly because we don't understand. We don't understand what's happening to make it variable, right? It probably has something to do with the clouds being patchy or not homogeneous, or the thicknesses change. But that's something we're still trying to work out. I can say that for the hotter objects, we do see spectral variability. For Daniel Pai at Arizona, the Lunar Planetary Institute, LPL, has an HST program where he's getting extremely high signal to noise time series spectra of LNT dwarfs. And he sees the spectra vary, actually. It's not dramatic in the sense that it goes from looking like an L and then turns into a T or something like that, but the water bands change and some of the atomic lines change. And depending on how you bin it up, you can say just do J and H. You'll see things out of phase, right? So the variability in the J band will have one phase, and the variability at another wavelength will have a different phase, which is suggesting that we know when we look at different wavelengths, we're actually seeing the different layers of the atmosphere, right? Just like in an atomic line, you're seing the different layers as you work your way along the atomic line. It's way worse when it comes to molecules. So you're seeing different layers, and the fact that they're not in phase suggests that the variability, they're not talking to each other. What's happening down here is happening independent of up here because they're out of phase with each other. So it does change what the spectrum looks like. If I had a spectrograph that could do it with this, I would expect to see it change, but that's not going to happen anytime soon. So I don't know that we'll ever know the answer to that for these guys.
Peter?
So you showed us some of the spectra of the Y dwarfs and the Y zeros and the Y
Yep.
and the I think it's the J bang is
Yep.
framework. And I mean, okay, something like half a century of Morgan-Keane classification. It still seems kind of perverse to me to measure a width of this thing and then put it in this box and say, all right, we're going to round it off and just call it a Y1 and just discretize this continuous measurement.
Yep.
Is there a better way?
I will, in a second, argue heartily for no, but I have people who disagree with me. Rebecca Oppenheimer at the Museum of Natural History is very much opposed to spectral classification and thinks it's a waste of time. I would argue quite strongly against that, and for the following reasons. First, what we're after is physical properties, right? Who cares about letters, right? What we want is the temperatures and the gravities and the radii. The problem is that nobody measures that directly. If we measured it directly, that's fine, right? So if you have an interferometer in your backyard, you can measure it, go for it. I don't care what the spectral tip is, I want to know what the radius is. But until that happens, right, you have to use models to do that. Which means that if I derive the radius of this object and I say it's 0.9 Jupiter masses, I have to put a date on it, I have to put a model grid on it, I have to put other things on it. And then the next person that publishes has to come along and say, okay, well I changed this little bit in the model, and so it's a year later, and it's this. And then you have this long list of various radii with various tags to try to figure it out. And so what I would argue the thing to do is call it something and say that's what it is, and then you let the models slide around underneath it, right? And a Y1 is always a Y1, and the temperature changes as the models get better, right? And so that's one of the reasons why I would argue you do spectral classification. Because it's and other reasons, it's a shorthand way of talking about things. When I talk to other brown dwarf astronomers and I say a T4, that means something to them, right? There's a median property of a T4, right? And then it's a great way of looking for outliers. If you have, this is what a T4 looks like, and then you plot a spectrum on there, and it kind of looks like a T4, but it's not really, you're going to learn something about that. And then you can say T4 peculiar, and someone will go, oh, okay, so it looks like a T4, but not really. And we'll say, and I know, if you look at some of the classification papers, it gets a little insane with all the letters and symbols after, but they mean something, right? They have value, I would argue. So no, I don't think classification should go the way of dinosaurs. I think it's a very useful thing. I think the reason why MK has stood for this time is because it's still valuable. Right? I would imagine the temperatures of A stars are still changing, right? And so an A0 is an A0, and it will always be an A0, right? And then someday when we have infinite knowledge about the universe, we'll know what the temperature of an A0 is on average, and then we can stop using spectral types. That's my argument.
Tony?
If I understand your charts correctly, the surface gravity of these things is much, much lower than, say, Jupiter or the Sun?
It's higher. So, well, okay. Sorry, you got me on multiple brown dwarfs here. The Sun is it 3? I think log G of 3, is that right? Somebody remind me? 3?
Oh.
I think it's 3. Or is it 4?
4.4.
4.4. Okay, so of order or higher for the hotter ones. And then for these colder ones, yeah, they're sort of order the Sun and lower. But if you go to the higher mass, hotter brown dwarfs, they can get up to 5, 5.5, depending on where you are. So it's sort of a range of 4 to 5.5, depending on the temperature.
I think for the mass function of brown dwarfs,
Yeah.
Looking at young clusters gives you the best idea of how it's varying, because one, you get rid of the age degeneracy because
That's
they're
right.
all very young and they're 10 magnitudes brighter.
That's right.
Even after you go down to a couple of Jupiter masses, you go to KO16, you can detect them.
Absolutely. I think part of the trouble with that, of course, is then converting those to masses, right? You've got extinction. You've got to worry about all these infrared excess.
I mean, the detailed structure, you have to worry about that, but the models are pretty good now, I would think, because they're harder.
Yes.
And you're not going to have quite the same.
Oh, and from that point of view, yes. Okay, I could see that. That's right.
Also,
I mean,
you're counting.
absolutely.
If
Absolutely.
they're only 50, they're only 50 no matter how you
That's
price
right.
the mass.
Yeah.
That still gives you a
Yeah.
strong constraint.
That's right. Yeah. And I didn't say this, but I think it's sort of, it's not a scientific reason. Well, maybe it is a scientific reason. I think it's important to know our solar neighbors, right? The fact that Kevin Luhman found 2 objects in the last 2 years that were 2 parsecs away, that's, when I give public talks, I start out with the Hubble Deep Field, and I say, we can stare to the edge of the universe, And yet, if you look at the solar neighborhood, we've added 2 new members in 2 years, right? So don't think that just because we can look deep, we know everything about the universe, is sort of my argument. So, I think it is important to look, because you could go to these places, right? Like, we can go to this object. Right? Let Chris Nolan go there instead of the black hole, right? So I think it's important to find these things. But I don't put it in a science talk because it's, really. Yes?
Is there any hope of separating out variability over the surface at one time from temporal variations by, for example, getting the period and then looking at the same phase repeatedly and things like that?
In principle, that's true. That's possible. Ian Crossfield actually did Doppler imaging of lumens 16A and B. So one of Kevin's binaries is a binary L and T dwarf. It's one of the ones at 2 parsecs. So it's really nearby and it's really bright from a brown dwarf point of view. And so he actually did high-resolution K-band spectroscopy, like 30 or 67, I don't know, it was cry-res down in the VLT. So really high resolution, and did Doppler imaging and actually has a surface map of the structure of B, of the B component. And it was in Nature or Science, I can't remember which one it is, but you can go buy the little cube thing, right, that you can put together and make a brown dwarf surface. So yes, except that's the one, right? And I don't know that anyone has thought about, the issue for what you suggested was, how does it evolve on longer timescales, right? And for example, for these Y dwarfs, we've already found that things change on months timescale. So you'd have to do this sort of very rapidly and get a lot of telescope time to do this, right? I mean, you have like an 8-hour period.
You have to separate out the period.
Yes, that's right, that's right. Yeah, I mean, once you know the period, you could do that.
Yes.
But in order to see it multiple times, you'd have to get data multiple times. And if the rotation period's 10 hours, that's a lot of Spitzer time, right? And I think we got our lot already. I don't know they're going to give us more time, that much more time. But yeah, in principle, that could happen.
I just wondered whether, in practice, it could be practical. And you were saying
Not anytime soon, I would say. No, not anytime soon.
Okay, we have time for a last question here.
Why do you think that the forward modeling you did is not very sensitive to the history of the formation of the objects? Because when you showed the plot of the age mass degeneracy that you were worried about, it looks like the age really does change it. So
Yes.
what's averaging out there?
It's, I don't know that I can tell you what the underlying averaging out is, but I know that when Adam Burgasser first ran these kinds of simulations in 2004, he did different star formation histories. He did exponential decay and he did stochastic. And he found that those weren't the dominant thing controlling the shapes of what the mass functions look like. And that's as far as I'll go with that, because I don't know the details. I don't know, I mean, I've recoded it myself, but I don't know, I haven't tried different age distributions, let me put it that way. I took his work at face value and just assumed that I could ignore that for the time being.
Okay, let's think like that.